In this lesson, we're going to be looking at the transition metals. Now, the majority of the metals in the periodic table can be found in the transition metals. So, if we're looking at the periodic table, we are talking about this block here in the middle. So we've got group 1, group 2 metals, we have the transition metals here, and then we have group 3, 4, 5, 6, 7, and 0. So whenever we're talking about transition metals, we're talking about this central block of metals, which is where the majority of the metals in the periodic table are found. So what I'd like you to do to start with, 5 minutes, is to list all of the common metallic properties that we have already discussed and that you might recall from year 7 and year 8, and try and separate them into physical and chemical properties. So for our common metallic properties, I'm going to split this in two, and I'm going to have our chemical and physical properties on either side. So we'll start with chemical. Okay, so we have the fact that they form positive ions, that they lose electrons, or lose their outer shell electrons, and our physical properties, we have a variety of things we can have. So we can have shiny when polished, they are good conductors of heat and electricity, they are malleable, which means they can be bent into shape. They are also ductile, which means they can be strung into wires. They generally have high melting points, and they are sonorous, which means that when you hit them they ring, you get that ringing sound. And that's just some of the common properties of metals. Now, it's important to remember that not all metals have all of these properties, but the vast majority of them do. So one of the key differences between the transition metals and the metals in groups 1, 2, and 3 is that the transition metals are able to form ions with multiple charges. So for example, if we're talking about a metal in group 1, it's got 1 electron in the outer shell, and it will always form +1 ions. If we're talking about a metal in group 2, it's got 2 electrons in the outer shell, so it only forms +2 ions. The transition elements, however, can form different charged ions. So, for example, iron can become 2 plus or 3 plus. Copper, 1 plus or 2 plus. Cobalt, 2 plus, 3 plus. Manganese can be anywhere up to 7 plus. So with the other metals, the group 1 metals, the group 2 metals, it's very quick and easy to predict the charge of their ion based on their position in the periodic table. And that is not something that we're able to do with the transition elements. So just knowing that you have iron in a compound means that you can't necessarily work out the charge of its ion from the periodic table. Just knowing that you have cobalt or copper or manganese or any of these transition elements, you can't necessarily predict their charge from the periodic table. So what we need to be able to do is to work out their charge using either their name or using the anion that they're bonded with in the compound. So for example here, I've got 2 different ions of iron. I've got iron 2 plus and iron 3 plus, and both of them combine with oxide ions to form iron oxide. And you'll notice that they form the same compound, they're both iron oxide, but they have different formulas. So transition metal ions can have different charges, and that means that they can form compounds with the same element but have a different formula. So the reason they have a different formula is because ionic compounds, just like atoms, need to have no charge overall. So in an atom, you have the same number of positive protons as you do negative electrons. And it's the same with these compounds. If you've got a positive ion and a negative ion, the charges need to balance out to zero. So here, where the ion is 2 plus and the oxide is 2 minus, that balances to zero. So the formula is FeO. But here, where the iron is 3 plus and the oxide is 2 minus, that doesn't balance to zero. So what happens is you have 2 lots of the iron 3 plus, which makes 6 plus, and 3 lots of the oxide 2 minus, which gives you 6 minus, and 6 plus and 6 minus does balance to zero. So what we do to make it easier to work out what the charge of the ion is you can either look at the name, and if it's a transition element, what they'll do is in brackets and using Roman numerals, they will tell you the charge of the ion. Now we know that these are all metals, so we know they're going to be positive. So copper 2 oxide, the copper will be positive 2. Copper 1 iodide, the copper will be positive 1. The non-metal that they're bonded with, we can still predict that the same way we would before using the periodic table. So oxide or oxygen is in group 6, so it's going to be -2. Iodine is in group 7, so it's going to be -1. So what I'd like you to do is to just write down the formula and the charge of the metal in each of these compounds and the formula and the charge of the non-metals in each of these compounds. So having a look at this one then, so copper 2 oxide. So we know it's going to be copper, and we know it's going to be positive because it's a metal. And because it's copper 2, it's going to be positive 2. Here, copper, again positive because it's a metal, copper 1, so it's +1. Manganese, +4. Cobalt, +3. And vanadium, +5. The non-metals they're bonded with, we can work that out from the periodic table. So oxide, oxygen, that's in group 6, so that's going to gain 2 to get a full outer shell, so it's going to be oxide -2. Iodide's in group 7, so it's going to gain 1 to get a full outer shell, that's going to be iodide -1. Oxide again, -2. Sulfide, sulfur is in group 6, needs to gain 2 to get to 8, so that will also be -2. And then oxide again, -2. So other than what we've already stated that the transition metals can form ions with different charges, what also sets them aside from the other metals is that when they form compounds, those compounds tend to be colored. So they form colored solutions and colored compounds. So they're really useful. So transition metal compounds are really useful in dyes and pigments and paints because of the color that they form. The other thing that they're very good at is they're very useful as catalysts, so they can be used to speed up the rate of a reaction. Now, other than that, you might be asked to compare the transition metals to the group 1 metals. Now, it's important to remember that the group 1 metals are very soft, they're very, very reactive, they've got quite low melting points compared to other metals. So when making those comparisons, you just need to remember that transition metals are harder and stronger than the alkali metals, they're more dense than the alkali metals, and they are less reactive than the alkali metals, and they have higher melting points than the alkali metals. So what I'd like you to do now is to use a double bubble map to compare the similarities and differences between the group 1 metals and the transition metals. So our similarities, you're going to look for the common metallic properties that they both have, and then we're going to look at what properties are unique to the group 1 metals and which properties are unique to the transition metals. So we'll start with the similarities. So they both lose electrons to form positive ions. They're both malleable and ductile. They are both shiny when polished. They're both good conductors of heat and electricity. So let's look at some of the things that are different about them. So the alkali metals are very soft. The transition metals are very hard and strong. The group 1 metals are very reactive. The transition metals are not very reactive. The group 1 metals form +1 ions. The transition metals form ions with different charges. The transition metals form colored compounds. Whereas the alkali metals form white compounds or colorless solutions. So some of the other things we could say about the transition metals, we could say they are more dense, therefore the alkali metals are less dense. The alkali metals have low melting points, whereas the transition metals have high melting points. And finally, the transition metals make good catalysts. So we've got lots and lots of information there, lots of similarities, lots of differences. So in the moment, you're going to see a video of the practical where we can identify whether a compound contains a transition metal or not using the color of that compound. So what we have are some metal solutions containing metals, some that are transition elements, some that are not. And what we're going to do is add sodium hydroxide to them. So we're going to add sodium hydroxide to form sodium hydroxide, magnesium hydroxide, copper hydroxide, iron 2 hydroxide, and iron 3 hydroxide. And what we're going to do is record our observations of those reactions and then use the observations to predict whether we think that they do or do not contain transition metals. So here we're going to look at some solutions containing metal ions, and some of these metals are going to be from groups 1 and 2, and the others are going to be transition metals. And hopefully from their observations of how they look, their appearance, and how they react with sodium hydroxide, we'll be able to distinguish clearly whether they are or are not transition elements. So we've got sodium sulfate, which contains sodium ions. I've got magnesium sulfate containing magnesium ions. I've got copper sulfate containing copper ions. I've got iron sulfate containing iron 2+ ions. And I've got iron sulfate containing iron 3+ ions. So if we look at their appearance first, we've got the sodium sulfate, which is a colorless solution, the magnesium sulfate, which is a colorless solution, the copper sulfate, which is a blue solution, the iron 2+, which is very faint, but it's a very pale green solution, and the iron 3 plus, which is sort of this greeny yellow solution. So just by looking at them, we can see the sodium and the magnesium are colorless, and the other three are colored. Even though the iron 2 plus is very pale, it does have a very pale green color. So we should be able to look at the periodic table and see that copper and iron, they're both transition elements. So we would expect them to have colored solutions, colored compounds. The sodium and magnesium, well, they're group 1 and group 2, and again, they are not transition elements, and it's only transition elements that form these colored solutions, these colored compounds. So we would expect the sodium and magnesium to either be colorless solutions or white solids, whereas our transition elements are going to be colored solutions and colored compounds. So if we add some sodium hydroxide, we can see more clearly whether they are or are not transition elements. So if I add some sodium hydroxide to the sodium sulfate, it remains a colorless solution, which is to be expected because it's not a transition element. If we add some to the magnesium, we get a white solid being produced, a white compound. Again, is to be expected because it's not a transition element. If it's not a transition metal, then we would expect colorless solutions or white solids, white compounds. The copper, if I add sodium hydroxide, gives us this dark blue solid. So it's a dark blue compound has been formed. Again, that makes sense, being a transition element. The iron 2 plus gives us this green solid. Again, makes sense, transition element. And the iron 3 plus gives us this sort of rusty orange, rusty brown solid being produced. And again, that makes sense because it's a transition element. So you can see very clearly that if it's colorless solution or a white compound, then it is not a transition element. But if you get a colored solution or a colored compound, like we do here, blue, green, and this sort of orangey brown, then that is much more likely to be a transition element. And another thing that's quite clear here is look at the iron. The iron here it's 2 plus and here it's 3 plus. Now, if we look at group 1, sodium, that can only be plus 1. Group 1 elements can only form plus 1 ions. Magnesium's group 2, it can only form plus 2 ions. But the transition metals, they can form multiple different ions. So iron could be plus 2 or plus 3. Copper isn't always plus 2, sometimes it's plus 1. So because they're transition elements, they can form ions with different charges. They form colored solutions, they form colored compounds, and we can identify them very quickly by looking at the appearance of these solutions and compounds. So what we should have seen when we added sodium hydroxide to the sodium sulfate is we had a colorless solution. And if we have a white compound or a colorless solution, then that tends to mean we do not have a transition metal. The magnesium sulfate gave us a white compound was formed. And again, white compound or colorless solution means it does not contain a transition metal. The copper sulfate, we got a blue compound formed, which means yes, it probably was a transition metal. The iron 2 sulfate gave us a green compound. Again, yes, contains a transition metal. And the iron 3 sulfate gave us that sort of orangey brown compound, sort of a rusty color. And again, meaning yes, does contain transition metal. And we can cross-reference those to the periodic table. Well, sodium is in group 1, not a transition metal. Magnesium is in group 2, not a transition metal. But copper and iron, both transition metals. And also the iron is able to have ions with different charges because it is a transition metal. So finally, there is a 10-question facts test. You're going to have 5 minutes to get this done, so that's going to be about 2 questions for every minute, so 5 minutes to answer these 10 facts test questions. Right, so just going to go through this quickly. Green pen, anything that you got wrong, and give yourself a score out of 10 at the end. So an element that has 2 shells and 1 electron in the outer shell. So quick look at the periodic table. So we're looking for something that's in period 2 and group 1. So period 2, group 1 is lithium. An element that has 3 shells and 7 in the outer shell. So that is period 3, 1, 2, 3, and 7 in the outer shell is group 7, which makes it chlorine. What name is given to a substance that contains more than one type of atom chemically bonded? That is a compound. What name is given to the smallest part of an element? That is an atom. Now, even though atoms can be broken down into smaller subatomic particles, an atom is still the smallest part of an element, because once you break it down into protons, neutrons, and electrons, they're no longer that element, because remember, it's defined as an element by the number of protons in the nucleus. What is the link between the period number and the atomic structure? Period number is equal to the number of shells. How many electrons does an ion of oxygen have? So oxygen has an atomic number of 8, so it's got 8 protons and therefore 8 electrons. It is a non-metal in group 6. It needs 2 more to get to 8, so it's going to gain 2 electrons, meaning that as an ion it will have 10 electrons and will have a charge of 2 minus. Which subatomic particle was discovered last? It was the neutron. So remember, the electron was discovered first, then the proton, then the neutron. How many electrons does an atom of oxygen have? Well, that one's going to be 8, because an atom of oxygen has 8 protons and therefore 8 electrons. What name is given to the rows in the periodic table? They are called periods. And name 2 properties of transition metals that are different to group 1 metals. So there's lots we can choose from. So I'm going to go with different charged ions. And they form coloured compounds. But any of the differences that we noted from our double bubble map would be fine here. So you could have they are more dense, they're less reactive, they're harder and stronger, all of those things that we listed in our double bubble map. Any 2 of those would be suitable to get you the mark here. So any corrections you need to make, do that in green pen and give yourself a score out of 10.